Hi everybody. This lecture is for the 29th of January 2020. This is class number 7 on Wednesday that had to be canceled because of some meetings. So just as an announcement, we will be back in class at our normal time and our normal location on Friday the 31st of January. Also, regarding homework number 3, we've already covered StormCAD in the class from Monday. In this lecture, there's going to be an example that will help to address the stormwater detention parts of that homework assignment. So that assignment, homework number 3, should be uploaded to Blackboard before class on Monday, February 3rd. So today we're going to be starting to talk a little bit about how stormwater is managed in an urban environment, some of the measures that can be taken to mitigate the effect of urbanization, and how to store the water so that it doesn't cause damage and scour to the receiving bodies that have stormwater runoff. The majority of this lecture was recorded in a previous semester, so there may be some incidental references to a time or a place that doesn't quite match up. But these announcements that you see here on the screen right now, these are the ones that govern. And if you do have any questions related to the material, you can send me an email. On Friday's class, when we get back together in person, we'll work another Excel example with stormwater detention and extend it into some other empirical methods that have been developed to estimate required stormwater detention volumes. So we'll continue the subject on Friday, but for now, let's begin discussion of stormwater detention.
Remember that urbanization has the effect of making the peak higher and come sooner than it would have in the natural state of the land. And the reason for that, the difference between before urbanization and after urbanization, is that by adding impermeable surfaces inside of the watershed, we're speeding up the flow of the water over the surface of the land. Because when water is flowing over like a grassy surface or flowing over forest litter, there's a lot higher roughness value than water flowing over smooth pavement. And so, number one, we changed how quickly the water is able to move over the surface, and especially when we add channels in. If you think about a gutter or a pipe, water is able to flow much more efficiently through an engineered conduit than it can through a natural channel. And then the other half of that equation is that in addition to speeding up water, you've also, through urbanization, you've increased the amount of impermeable surfaces. And so a gravelly area or a vegetated field in the past would have a relatively low C value, which means a lot of water is infiltrating. But when you urbanize, the march is inevitably to put in roofs, asphalt for roadways, parking lots, and sidewalks or concrete, and none of that infiltrates water efficiently. So the runoff hydrograph is the peak is sooner and higher. This figure is showing two things. The hydrograph, which I've just shown you, above that, this is called a hyetograph, a rainfall hyetograph. And so the hyetograph, this one, is breaking the rainfall up into distinct periods. Rather than measuring it continuously, they're reporting an average during a certain period. And so it may be that this storm was 3 hours long, and during the first hour of the storm there was a certain intensity, and then the rainfall intensity went up for another hour, and then the rainfall intensity went down again. What this rainfall hyetograph is showing is what fraction of the rainfall back in the olden days used to infiltrate. And so all of the water underneath this top line, so before urbanization, all of that water infiltrated. And I'm going to write a conceptual formula on the whiteboard here, and it is rainfall excess equals rainfall minus infiltration. Another word for rainfall excess is runoff. Okay, so conceptually what this means is that before urbanization we had lots of infiltration for the same amount of rainfall, assuming that stays constant. If you had more infiltration back in the olden days, before we paved over everything, then that meant during those olden days there wasn't as much rainfall excess as there is now. So developments like, that Amazon customer service center, that used to be natural land. You put a big warehouse and loads of parking up on that hill, then the people downstream of that hill are going to see more flooding than they used to. So if you live out in the countryside and it just somehow seems like the creeks are higher than they used to be, it could be that there's development in your watershed. And the reason why is there's less infiltration, and for the same amount of rainfall, then there's going to be more rainfall excess. So what this figure is showing is that after urbanization, now there's less of the area under that curve devoted to infiltration, so more of it is going to be the rainfall excess. Okay, so what we're trying to do in stormwater control is mitigate those effects. And there's a variety of ways of doing it. We just have to think a little bit differently, and the goal is always to try and delay water's arrival to its ultimate outfall. And by outfall, I mean maybe the water's going to a creek, maybe it's going to the Ohio River or to a lake. We just always want to slow water down when there's a storm, and as much as possible encourage infiltration. So what this best management practice is showing is a vegetated filter strip. So what that is essentially is just a grassy area by the side of the road where water is forced to flow over the surface before it gets into the ditch. They could have put a ditch or a curb immediately adjacent to the roadway, but by doing that, you're immediately channelizing the runoff. Instead, it's better to have a little bit of sheet flow before you go to channelized flow, because channelized flow is fast. When you've got a depth of water, it can move with less resistance through that channel than if it's flowing as a sheet. So you just think, what kinds of flows are slow, sheet flow? What's going to improve infiltration? Vegetation. And so that's the idea of a filter strip. And this is showing it next to a roadway. There are places where they do the same thing in a parking lot, where just putting in patches of grass in a spot where peak cars aren't going to be parking can have an enormously positive impact. And also it improves the water quality as well. This figure is showing if you have a stream and you have a filter strip before that stream, it's called a filter strip because the water quality is improved if the type of water that comes off of roadways, it has oils, it can have some of the hydrocarbons from fuel. Salt is applied to roads and sand for grit to help people get traction. And none of those things have a positive effect in the aquatic ecosystem. All those things have negative effects. So if you have that water flow over grass, then the grass can extract some of those pollutants and the sediments can settle down into the grass. And so it's better to have the pollutants hit the grass than it is to hit the stream, because the organisms that are in the stream are more sensitive. All right, here's another illustration, and this is something that's been pretty hot in Huntington for the last 5 or 6 years, is trying to get people to disconnect their roof drains. And I previously already told you about our combined sewers here in Huntington and how about half of the network has both wastewater and stormwater running through the pipes. And when it rains, that stormwater makes its way into the streams and pushes the wastewater along with it. And so if you disconnect the, If you disconnect the roof drains, then you're going to be reducing the amount of water that gets into the combined sewer. Now, people are worried about flooding their yard. You're not supposed to put runoff water next to your foundation because it can damage the foundation as well. But all it takes is a little bit of an extension on the drain to get the water away from the house, and things can be completely fine. There's going to be sheet flow, there's going to be more infiltration. Sometimes they take this disconnection to the next level, and the next level approach is if you enhance the infiltration capacity of the soil. And so if you kind of extract a clay soil and you put in sand or otherwise amend the soil with little plants, then that can be another way of disconnecting your roof drain, but then also encouraging even more infiltration than there ordinarily would have been. You can see that there's a bit of like a dam edge around here. So they're kind of making a temporary pond when it rains in their yard. So that could be kind of nice, a little ecosystem in your side yard. Here's showing that filter strip idea in a parking lot. They call it bioretention. If you are selective in the types of plants that you put in, if you make sure that they're native plants and plants that can extract a lot of water from the ground and try and increase the amount of evapotranspiration, then that's a favorable thing. So bioretention is another BMP. That acronym BMP means Best Management Practice. And it's a term used in a lot of different industries, but in terms of stormwater, these BMPs are different ways to promote infiltration and delay runoff. So here's another one. Trying to make it so that concrete absorbs more water than it ordinarily would. And so one approach is to use concrete pavers and packing gravel in, where it used to just be a continuously impervious surface. Now you've got a little bit of impervious surface with the paver, like this might be a cinder block that then you reinforce with gravel. And so there's going to be better infiltration there than there would just be for pure concrete. And speaking of concrete, let's see if this YouTube video is still up. It shows some porous concrete. Because if you think about it, if this isn't well drained, if the subgrade beneath the concrete isn't well drained, if there's water backing up and it freezes, it's just going to break that apart, no problem. And so I think the key to good porous concrete is to have some slope to it and to have big pieces of gravel, like a thick gravel layer underneath, so that the water can really move through and get out before it freezes. Yeah? Yeah, that the whole town of Huntington would benefit, but it doesn't have the longevity, the proven longevity that ordinary concrete does. And we have enough trouble just with ordinary materials. To switch to something more fancy would be a challenge. But I think it's a great application for like a university. This was at the University of New Hampshire. And so universities generally have a little bit better maintenance than cities do, because you got to keep the university nice or people won't come here. You got to make it like tourable condition. So that's an illustration of like different ways to just think of paving in a new way. Okay, a grass swale, that's a fancy name for putting grass in the ditch. So why would a grassy ditch be better when it comes to fighting the effects of urbanization? Why is a grassy ditch better than just a dirt ditch? Slower. Exactly. Yeah. It's because this grass sticking up into the flow has a higher end value, so the velocities are going to be decreased. Also, there's the advantage of the grass is going to keep the sediment in place. And so scour and erosion is a real problem in streams. And so if you can get grass to grow because you've got enough sun, in a lot of places here this wouldn't work because you've got a tree canopy over the ditch, and so there's just not enough sunlight for the grass to grow. But there are spots where it will, and where it does, it helps to prevent the channel from being damaged during big peak storms. Okay, here just promoting new ways of having additional infiltration. What this is showing is this is a pond, a local pond in a commercial development where the runoff from this parking lot is going towards the pond, and what they've done is they've dug out the center of the pond and amended the soil there. Instead of just having it be the whatever soil it was initially, they've put in gravel and where the water can seep down to the subsurface more easily. Regenerative stormwater conveyance channel. Instead of having a straight line that the water just flows downhill, by having a series of pools, what happens during a storm is if these pools were dry to begin with, the first pool has to fill and overflow to the second pool before any of the water makes it downstream. And if you think our whole objective here is to delay how quickly the water can move from one spot to another, this was a relatively steep channel to begin with, and so the water would have been very shallow and moving quickly over that surface. There's probably a good chance of scour or whatever the material was. And so the idea here is that you build up a series of smaller pools, each of which have to fill before there's any movement towards the creek. So that really reduces the damage to the surface for steep slopes. Rainwater harvesting is becoming kind of common. Especially in Australia, they do a really good job of capturing rainwater off of roofs. Here in Huntington, they've done that. Do you know where Latas is on like 4th Avenue? Or maybe it's where it used to be. I think it might be closed now. But they have a big tank like this where they were capturing the stormwater off of their roof. And the plan there was to use the stormwater for watering the flowers in Huntington. Yeah.
That was illegal to take the water that came onto the roof and recycle it.
Nope, it's not. Nope. And in fact, here in Huntington, they were buying rain barrels for people for a while. I don't know if that program's still active, but the city of Huntington was paying for people to disconnect and to attach rain barrels. If it's illegal, let them arrest you. Good thing to go to jail for. All right. Here in the engineering building, we've got a vegetated roof, and so you've seen those if you've peeked out the door. I don't know why they've got those doors locked. It would be better if it wasn't locked. We could have barbecues up there and smoke and stuff, you know. All right, we got to zip through these, otherwise we're not going to get to the stormwater sizing. Filtration practices just acknowledges the fact that this is a gasoline station here, right? This is obviously a filling station, and these sorts of places are notorious for even just a little bit of spill onto the ground for each car is going to put a serious amount of hydrocarbons, and the pollutants in that, like benzene, toluene, xylene, BTEX, those pollutants are carcinogens. And if they get into the water, that can infiltrate down into the groundwater. It can have effect on the fish and the birds and the insects that live in streams. And so finding ways to capture especially polluted water like that at a filling station is important. So it may be something like a passive filtration where just by gravity you're separating oils from the top, sediments from the bottom, and maybe a separate pond where the organics can vaporize out before they get into a stream. A constructed wetland is becoming quite popular because constructed wetlands have a way of improving the water quality. Constructed wetlands are like a stormwater pond that's meant to always have some water in it. We'll look at some sketches, some hydraulic sketches of the types of fittings you'd need for an extended aeration basin versus a constructed wetland and so on. But here, biological uptake of nutrients is really important because sometimes the pollutants aren't necessarily just limited to heavy metals and sediment and organics, but sometimes just nutrients like nitrogen and phosphorus, which a farmer may be adding to a field in one location, so it can be beneficial for agriculture because it stimulates the growth of beneficial plants in a crop area. But when those pollutants run off and get into a stream, then they can have really harmful effects, and there's been a lot of talk lately of red tide in the Gulf Coast. If you've heard about that, what it is it's when nutrients get into the ocean, it stimulates the growth of bacteria and algae. And those bacteria and algae, they consume not only just the nutrients in the water, but they also consume the oxygen. And so there will be these what are called dead zones in the ocean where there's no dissolved oxygen, and it causes fish kill, and it can be pretty nasty, the breakdown of organic constituents in the absence of oxygen, the anaerobic consumption of organic material can form like hydrogen sulfide, which is corrosive, and we've talked about how it's dangerous for humans when it's in pipes and in an enclosed environment. So constructed wetlands has the advantage of nutrient removal because what you're doing is you're stimulating the growth of plants like cattails and and trying to have aquatic weeds grow. And sometimes you may need to harvest those aquatic weeds in the constructed wetlands and dispose of them in a landfill. But it's a lot easier to do that than to allow the polluted water to make its way into a protected stream. Okay, detention ponds is the bulk of what we're going to be talking about for the rest of the lecture today. And a dry extended detention pond is dry because it doesn't have water in it on a continuous basis, in contrast to a constructed wetland. A constructed wetland is always meant to have water, but a dry extended detention pond is only going to receive and have stormwater during the stormwater event itself. The wet pond is a little bit more like a constructed wetland. All right, so remember, here's our hydrograph and hyetograph. A hydrograph is a figure depicting runoff. A hyetograph is a figure depicting rainfall. Stormwater ponds exist to mitigate the effects of sooner rainwater runoff and more of it. So the problem we're trying to solve is that there's more volume of runoff and it's coming faster, and the pollutants that can occur in an urbanized environment. So we're trying to make the after look more like the hydrograph was before urbanization. There are a couple approaches to doing that. You can try and prevent the water from getting into streams in the first place, and that's often called source control. So source control may be regulations like was levied on Cookout, where they had to put in that special pervious pavement because the city doesn't want the runoff from their restaurant getting onto Fifth Avenue. And so that would be an example of local disposal. Another example of local disposal would be in a shopping development, how they have to set some of the land aside for a pond. And so if you've ever been to Target before, and as you're driving up to Target on the left side of the road, there's a really big, significant stormwater pond on the left side there. It's super deep, and they've got a chain link fence around it because when it fills, it's going to be very deep, and they, I guess, don't want kids getting in there splashing around. So those are illustrations of trying to hold on to the water and delay it as close to the source as possible. Downstream control is talking about measures where the water has already come to a point of concentration, and now you have to build a much larger stormwater detention facility. And so that big cavern in Japan, the concrete vault that they had, that's an illustration of downstream control. An extended detention basin is one that is intended to have water just on a temporary basis, and so the perforated riser is the holes are at the bottom of the pipe. So water comes in, and if the inflow to the pond is greater than the outlet flow, then the pond is going to start to fill. But it's not until the water gets to the spillway that the water can go through the outlet in kind of an unregulated fashion. A little bit can trickle in through these perforated risers, and some is going to be coming through the outlet. But the purpose of this primary spillway is it would be basically a vertical pipe, and the water can enter this pipe without restriction once it gets to the maximum storage level. The purpose of a circular baffle around the primary spillway is just to keep grease and sticks and other debris from getting into the outlet pipe. Typically, an extended detention basin would be used for situations where you expect the pond to have water maybe about a day or perhaps a little bit longer. And the environmental benefit it has is it's settling particulate pollutants. But the problem is that there can be a risk for mosquito breeding if the area stays moist for too long. In contrast to the extended detention basin, look at where the perforated riser is. Now, in the case of a retention pond, the perforations are at the top of the pipe. So no water is going to be leaking out during the storm. It's only when the water level gets above those perforations that the outflow will begin. And so a typical residence time, the average time the water particle spends in the pond would be 2 to 4 weeks. And that's selected because what we're hoping for is a much longer treatment time for the nutrients to be removed by whatever plants are growing inside of there. And the process of photosynthesis is extracting some of the pollutants and causing plant mass to form. And a part of that plant mass is the phosphorus and the nitrogen that was dissolved in the water. So this has the advantage of a biochemical removal of dissolved nutrients. But the issue here is that this extended detention basin is dry most of the time, and so it's much easier to maintain. You don't have to drain it to maintain it. You just have to occasionally, if there is a lot of sediment at the bottom, you could send a crew in there with a backhoe or some sort of shovel and bucket and remove the sediments. But in the case of the retention pond, it's going to be a much larger effort to completely drain the pond, and then you've got probably like a benthic muck, like an anaerobic breakdown of organic material at the bottom of the pond since it's always submerged. So that can be a little bit nasty. The risk of anoxic conditions means that there may not be dissolved oxygen at the bottom of the pond, and so there is the possibility of hydrogen sulfide formation, and kind of worms and insects that form in a low oxygen environment are generally considered to be kind of a little bit undesirable. So how big should the pond be? This figure is showing that the pond is storing the difference between the inflow hydrograph and the outflow hydrograph. So look at what we've got is over time the discharge of the pipe that's feeding the pond, which is the inflow curve, and then the outflow curve. So the pond is going to store the difference between the two. So its accumulation is in minus out. So this V sub S is the accumulation inside the pond. So ideally what we'll have is an inflow hydrograph at high resolution, at least hourly increments. And the more frequently, then it's better, because what we're doing kind of is a numerical integration. We'll calculate the volume into the pond during some time increment. We'll calculate the accumulated volume up to that point, and then we're going to find out how high is the pond, because it's the pond depth that dictates the flow out. In most cases, what these ponds have is just an orifice, and so it's going to be the orifice equation that says the flow rate out from the pond. And then we do this hour by hour. We see how much came in, how much flowed out, what was the depth that dictated the flow rate out, and so on. Okay, so here's an illustration. We're going to go through and with Excel size a pond and find out what's going on here. Just for simplicity, let's assume that this detention pond has square edges. Now, that's not realistic, but the geometry is a little bit simpler for this first exposure to the method. More realistically, what we'd have kind of like a trapezoidal shape of a pond. It's sloped at the edges instead of being straight up and down at the edges. But just for simplicity, let's say we've got water coming in. Here's our inflow hydrograph in terms of cubic meters per second over time. And what we want to do is find out what is the peak flow rate out of the pond for a certain size pipe. We've got a 250 millimeter pipe, and we're using the orifice equation. V is the square root of 2GH. And what I hope you remember from fluid mechanics is in the orifice equation, if we have an outlet, we measure from the center of the orifice, and H is the distance from the water level to the center of the outlet. And then that is what would tell us the velocity of the flow outward, the orifice equation. All right, so let's start up Excel here. I've got 11 minutes till my alarm goes off. Let's do this. All right. So we'll start with the blank workbook, and The pond characteristics here is it's a 65 meter by 65 meter. That's the top view of the pond. So 65 by 65, 0.25 meter diameter pipe. So the columns we're going to put in, let's go a couple of rows down, and then we're going to put in a column that's time, and then the inflow in terms of cubic meters per second. All right, the volume in cubic meters, and the accumulated volume in cubic meters. All right, the depth at this point in time, the H value, which is going to be slightly different than the depth because of the orifice, the outflow in terms of cubic meters per second, and then we'll have a column representing the volume out in terms of cubic meters. All right, let's see if we can figure this out. So our time starts at 0, goes 1, 2, and so on. We may need 23 hours to see what's going on here. Let's look at a 23-hour cycle. Our hydrograph that we were given is that at 0 time, the flow in is 0, but then we've got 0.3 cubic meters per second, then it goes to 0.67, then 0.81, 0.67, and 0.22. Let's just make sure, does that match the given data? Yeah. All right. Now up here at the top, let's just put some of the data that we know here, like the pond area in terms of square meters. The pond area, that pond was 65 by 65, so I'm going to do equals 65 times 65. Got the pond area. The outlet pipe diameter in terms of meters was, that was a 0.25 meter diameter pipe. And let's calculate the pipe area from that. Okay, we're doing pi times d squared divided by 4. Okay, it gives us the pipe area. And the C sub d is the coefficient of discharge. That's related to like energy losses as the water approaches that pipe outlet and goes through that pipe. And the C sub d that was given in the example sketch, it said it's 0.59. So we're going to use that when we calculate the outflow. Any questions so far on what we've got on screen? All right. So the volume in, V equals Q times the time. So it's equal to inflow times the number of seconds in an hour, 3,600. So there's no volume in yet, but if I double-click that formula and have it go down through the rest of the spreadsheet, for instance, during the hour 1, if the flow is 0.3 cubic meters per second, and we multiply that by 3,600 seconds, and that tells us there are 1080 cubic meters that flowed into the reservoir during that time. Okay, so our accumulated volume, it's 0 at first, so just 0 in time 1. At this next time, it's just what's come in so far, because there hasn't been any outflow yet in the first hour. So we'll just say it's 1080 to begin with. We may have to come back to that column later, though. We can't necessarily carry it all the way through. All right, so what is now the depth and the H? All of that's 0 when the flow in was 0. So it's hour 1 where things get a little more interesting. So the depth, if our accumulated volume is 1080, the depth is the volume divided by the pond area. Okay, so if there's 1080 cubic meters in that pond, and the pond has a known area of 4225 square meters, then the depth is just going to be 0.255 meters. Any questions about that or anything else so far? Here's our pond, and here's the outlet. So if this is the depth is from the bottom of the pond to the water surface. Here's H. H is from the center of the pipe to the water surface. And so what we have to do for H is we have to say it's equal to the depth minus the pipe diameter divided by 2. So we just have to subtract out half the pipe diameter from the depth. Okay, outflow. Remember, for the orifice equation, Q equals C sub D times the area of the pipe times the square root of 2GH. So this is the formula we're using for outflow. So it's equal to the outlet pipe area times the C sub D times the square root SQRT of 2 times G, 9.81, times H, which was this column F value. Mm-hmm. So we've translated this orifice equation, C sub D, area of the pipe, square root of 2GH. That's our outflow. And so if that's the flow rate out, then the volume out is the flow rate out times 3,600. I'm going to reduce the number of digits that are shown to something slightly less ridiculous. All right. Okay, so then, hour 2, accumulated volume. This is where we have to be a little bit careful here. So the total amount of water in the pond is the previous amount of water that there was, plus the new water that came in, minus the water that flowed out during the last time period. So this is why it's good to use small time steps. Is the smaller the time steps are, the better this numerical integration works. But we're using the volume out during the previous time step. And so it's not perfect, but it's good enough. Does everybody get this? Accumulated volume? Let me do it again just to make sure. So what we're saying is, in the second hour, the accumulated volume is the previous accumulated volume. How much water? The accumulated volume is how much water is in the pond now. Okay, so the amount of water in the pond now is how much water was in the pond last hour plus whatever flowed in minus the volume that flowed out. And the best we know about the flow out was during the previous hour. That's our best estimate. So that's why we use the previous hour. Okay, so now we've got accumulated volume, and we can drag the rest of these formulas down. Everything else is just going to kind of be the same approach as the previous time. Depth is based on the volume. H is based on the depth minus half the pipe diameter. Outflow is a function of the orifice equation. Volume out, everything we can just drag down through the entire 23-hour time period. And what we see, hopefully, is that the water depth gets deeper and deeper, but then the pond starts to drain because the storm stops. At hour 5, there's no more water coming in. So now what we've got is it's draining. I've got 60 seconds left before this alarm goes off. So what I'm going to show you is how we would turn this analysis into design. What if there was a regulation that said, well, that's all well and good, but the water shouldn't be any deeper than 1.5 meters. So what would we have to do to get it so that the depth never goes higher than 1.5 meters? Okay, good. That would be one way. And would we want the pipe diameter to be smaller or bigger? If we want to limit the depth to 1.5 meters, would we want the outlet pipe to be bigger or smaller? You want to let more water out or let less water out? More. So one approach would be make the pipe bigger. Okay, let's do that. Let me change this outlet pipe from 0.25, let me change it to 0.5 and see what the maximum depth right now. I'm going to do this max function. 2, 1, 0. That's not a very loud alarm. All right, I'm out of time. So let's just do it 0.5, yes. Now the depth is smaller. The other approach would be make the pond bigger, increase the pond area.